My name is Harry Westfahl, and I'm director of the Brazilian Synchrotron Light Laboratory at the Brazilian Center for Research in Energy and Materials in Brazil. And I'm going to talk about how I use Wolfram Language to manage and to help building the large facility that we operate now. It's called Sirius. So my presentation, we are going to talk about Sirius and how I use this Wolfram Language for decision tool, basically using physics, exposing trade-offs and guiding instrument design and operations under, of course, tight time, budget, and risk. So first question is, why do we build a large facility such as Sirius in a developing country or anywhere in the world? So we have several reasons why we do that. First, as a large facility is a multi-user national facility, multidisciplinary, so we have people from everywhere. This is a democratizing science. We have advanced instrumentation access for under-resourced research groups, and which are also trained, and we help with capacity building through education and training and collaborative networks. This also helps fostering international collaborations across borders, across cultures. We have users using this facility from everywhere in the world. All the technology that we developed, and we developed national technology for this machine, had spin-offs in medicine and microelectronics and advanced manufacturing and others. All the companies that participated in the project, they actually used what they learned by building this facility with us into other areas. So that's what I call spill-offs. We drove regional innovation through that. So lots of local companies, they made the partnerships with academia and policymakers, and this created a really nice ecosystem of innovation in the country. And through the use of this facility, now that it's ready, we use it for drug discovery. We find drugs in the biodiversity. We use the synchrotron to investigate new molecules that can use for drug discovery in the large biodiversity Brazil has. And also to understand better soil properties and how to use and manage soil in a more consistent way that is also environmental friendly. And as you know, Brazil is one of the key countries in the world using clean energy through biofuels and through hydroelectricity. And so a lot of research on Sirius is also dedicated to that. And environmental monitoring, which is also a very large concern for everyone in the world now. And our largest project now is a response to epidemics. We're actually building a BSL-4, maximum safety laboratory in biology to investigate pathogens, and I'm going to talk a little bit about this. So first, let me show you, I'm going to show sneak peeks of Sirius in small movies. So this is to have an idea what the accelerator is. So it's a particle accelerator. We accelerate electrons. So this is a large infrastructure. We start by accelerating electrons from the rest where they are in thermal cathodes that we take the electrons from. And these electrons are accelerated first in the linear, so-called linear accelerator that you see now. So this linear accelerator is responsible for bringing the electrons up to 150 mega electron volts. So what you see here is an animation of the electron beam going through several structures that we designed. This was actually designed with the Chinese synchrotron. And what you see here is also a real image of this linear accelerator that brings the electrons to 150 mega electron volts. Then what you see in the right side of your screen is a booster. It's a synchrotron that is used to bring the electron energy to 3 giga-electron volts. So you see in this animation, the electrons, energy is boosted. So they are brought to 3 giga-electron volts. And once they have this nominal energy of 3 giga-electron volts, 3 billion electron volts, they are transferred to the main synchrotron. It's the storage ring. That's where we get the radiation from. So the objective of this machine is to produce electromagnetic radiation for experiments. So it's basically a very complex X-ray producer. It also produces infrared and ultraviolet and visible light, but essentially we use a lot of X-rays. So it's an X-ray machine. So how do we do that? The synchrotron parameters are, as I said before, 3 giga-electron volts, and we have a circumference of this machine of 520, almost 520 meters. It has emittance. It is a parameter that tells you how much of the phase space of the electrons in the storage ring is occupied, and a current, because these are electrons, and so they generate currents when they are transported. It's 350 milliamps is the nominal current. And just to give you an idea, 3 gigaelectron volts produces a Lorentz factor of contraction of almost 6,000. So all lengths from the point of view of these electrons are contracted to 6,000. And just to have an idea, this corresponds to this fraction of the speed of light. So 99.999999999% of the speed of light. And the electrons are, of course, not accelerated alone. They are accelerated in beams. The beams, they move. The electrons, they move more or less harmonically, transversal harmonic motion around this nominal orbit of the electrons. So this creates a kind of harmonic oscillators around the nominal orbit that creates an envelope for the beam size. And the smaller is the beam size, the better is your source. So it's the source of radiation that you're going to use to demagnify the source, use to make images, and the smaller it is, the finer is the detail of the image. What you see here, these are the parameters. The electron beam, it actually is expanding and contracting through all the magnets of the storage ring. So what you see here are the magnetic structures, and this kind of the envelope of the electron beam size. So you have points on the phase space where the electron beam size, which is basically the envelope of this structure, the motion of the electrons is more or less described as by deterministic forces from the magnetic fields and so on, and from the damping of the radiation. As the electron emits radiation, this motion is damped, and from the quantum fluctuations that happen when the electrons emit photons. So they diffuse through these random forces as well, and this, all in all, this motion gives this beam size for the electrons. So just to have an idea of with these parameters that we have, the beam size can reach something of the order of 20 microns by 2 microns for the electron ring, in the storage ring. So just to give you an idea of this motion of the electrons, so they keep running through these lenses, and they are bent, their trajectories of the beam. What you see here in blue is the electron beam, and then the white is the photon beam. Every time the electron beam is accelerated, so it's deviated from its trajectory, it emits radiation. So this is a dipole, and when this radiation is emitted, we can use for experiments. Now, the spectrum of this radiation can be calculated, and what you see here is the spectrum of this dipole. This is a 3.2 Tesla dipole that basically through the Lorentz force bends the trajectory of the electrons, and this creates radiation in a certain spectrum. So you see the peak of the radiations is at 20 kiloelectron volts. Just to give you an idea, 12 kiloelectron volts corresponds to a wavelength of 1 angstrom. So at 120 that you see here, this is 0.1 angstrom of the wavelength. Now, there are also weaker magnetic fields, like 0.6 Tesla, which has a different spectrum. And for instance, to obtain infrared and ultraviolet, we use those magnets because, as you see here, there's a gain in brilliance, in photon flux, as we move to this low field band magnet. So all in all, this is a system that accelerates particles to obtain radiation. Now, we can do better than that. We can move the electrons to a different orbit. So the same electrons can be moved to devices that make them wiggle. And as they wiggle, every wiggly is an acceleration, and each one of these wiggles emit radiation that are superimposed coherently. So these devices are called undulators. And to design these undulators, we have to use initially analytical models such as this. This is a so-called Halbach array. So the analytical expression for this magnetic field can be easily obtained. And from this, we can calculate the magnetic fields. And for instance, when we move these arrays and we open the gap in between these arrays, we can reduce substantially this magnetic field. So the electrons go from a wiggly trajectory to a straight trajectory when the field is 0. But we can also do what we do in Sirius, is to move the phase between these arrays. So as you see, as we shift the phase between the arrays, also we can change the magnetic field, because what matters for the electrons is the component of the field transversely in the direction of motion. So we can do that, and these are control knobs that we use in the different devices in Sirius. And to find the optimal region where the electrons can navigate and produce the pre-described energy range in the spectrum of the undulator, we have to map this field, so-called roll-off map. So these are fields where 0 is a nominal energy, and everywhere the electrons that navigate, they will produce energies slightly off from what we don't want. So this also helps on the design of this undulator and on the orbit and the tolerances. And if everything goes right, then you will obtain this brilliance. Note that instead of having this continuous flux of radiation in the undulator, we only have this harmonics, which corresponds basically to the emission of the electron when it's wiggling. You can think of the electron as an antenna. So once it's wiggling with the period of, let's say, centimeters, as you saw in the movie, this has Lorentz contraction of 6,000. So it goes from centimeters to micrometers. So in the reference frame of the electron, it emits infrared radiation. But there's the Doppler shift. And from the Doppler shift, again, a factor of 6,000 in Doppler shift that brings to X-rays. So that's how we obtain X-rays. It's just pure relativistic effect from the undulators. Now, once we get the undulators, then we have to refocus the beam into the experiment. So what you see now is the beam line. So the beam from the accelerator is brought to this set of instruments called the beam line. So the first element in a beam line is the so-called monochromator. The monochromator is a set of silicon crystals, typically, as you see here, that when we use Bragg diffraction to obtain the desired energy, then they are brought to these mirrors. These are elliptical mirrors that focus the beam into the desired spot and with the desired size. Now, for many of these experiments, we want to focus the beam as small as possible. We want to bring the beam down to a few nanometers, and this is equivalent to several very complicated calculations that we do through phase propagation of the beam and to a very detailed optics propagation. But we have to start from somewhere. So that's also where I use Wolfram Language. For instance, these are this detailed calculation that I just plotted the numbers here. And when we start, we have several parameters like the mirror lengths. When we move the mirror lengths, we have different vertical. And so this is what you see here is the beam size at the focal point in the vertical and the horizontal direction. And this is the diffraction limit if the beam was perfect. Now, if there was no beam size of the electrons when they emit the radiation. Now, if I move the fraction of the source, or if I move the vertical mirror or the horizontal mirror, I can bring to optimal conditions. And if I move correctly, and I can put the design teams to bring the most perfect condition for the beam. And once we find this condition, we tell them, okay, this is the ballpark of parameters that you have to simulate through detailed computations that may take several days. But with the Wolfram language, I can optimize this and I can search this parameter space and with more certainty. Now, once we bring this beam into the beam line, now comes the next step, which is really doing the experiment, hitting the sample and analyzing the data. Now, when you have this, the beam comes into the sample, it's focused there. We have, for instance, in this case, a crystal of proteins. And after collecting the data in the detectors and analyzing two different codes, we reach, for instance, in this case of this protein crystal, we reach the structure of a protein. And this is done in several ways. And when you think about the protein data bank and the Nobel Prize of last year, where that was given for AlphaFold, for instance, it was using this kind of data, right? And data from the structure of proteins that was accumulated in the protein data bank and was used with machine learning to generate this marvel that is AlphaFold. Now, I have one very good example of a protein that was found and its process of working was elucidated in our center. And it's this article published in Nature this year. It's called Metagenomic Dark Matter Enzyme Catalyzes Oxidative Cellulose Conversion. So basically, this is the protein that you see here. It's the structure of the protein. And these two little dots that you see here, these are copper atoms. These copper atoms, one of them is responsible for breaking cellulose, and the other one is responsible for generating peroxide, oxygen peroxide in the water, so that it produces enough electrons to the other one. It's almost like a battery charger for the other atom of copper to be in the right redox state to break cellulose. So this makes this enzyme really powerful in breaking cellulose. And one of the key applications of this is transforming sugarcane bagasse, for instance, which is a waste product, into ethanol. That is the fuel that we have in our cars here in Brazil. And this enzyme is the new state of the art in biomass production of ethanol and other goods. So basically, cellulose is a polysaccharide, and once you can break the small molecules, it can use for several things. And one of the things is fuel, like ethanol. So this enzyme and its structure was revealed with Sirius. Now, if we move on, of course, this is not the only kind of experiment. We have several other experiments. What you see in the video here are all the beam lines, these instruments that work different from protein crystallography, work with different other experiments. So there's a plethora of experiments that you can find on Sirius. These are our beam lines. So each one of these beam lines basically can do about 40 experiments per year in different areas of knowledge, using infrareds, using X-rays, using tomography, using spectroscopy, using different kinds of experiments to reveal microscopic details of matter. So basically, it's a big set of tomographers that you can look from the atomic perspective, or you can look from the micrometer perspective. Now, to get the beamline design, the beam on Sirius, the electron beam, is so small that the photons that propagate as X-rays, for instance, they are completely coherent. So another issue that we have to solve is how do we put those mirrors? Where is not only the size, but where we put those mirrors. For instance, depending on the aperture of those mirrors, we can get coherent fractions, mirror to source distances. We can have focusing procedures that are completely different, and manipulate it helps us a lot to put the beam in the right size. So we're talking about structures of tens of meters that are necessarily to be put in the right place. And each one of these beam lines was optimized in a different way, but basically what we have here is a periodic table of beam lines, what they can do, and what are the energy range, and what is the resolution, and so on. This is how we organize our instruments. Now, just the last is other kinds of experiments that we can do on Sirius, like, for instance, this is a prototyping of data analysis of tomography. This is a microaggregate of soil, and we're looking at basically one of the problems that we want to solve in soil sciences is there's a region of Brazil with a soil with a very strange properties. It becomes a concrete when it's dry, and no one knows why. So we are analyzing the pore structure of this soil, and what you see here is how we can use Mathematica to prototype the kind of tomography, and not only that, but also to look at the composition in different beam lines. So these dots in red are iron, in green are titanium, and blue are zinc, and we can actually do the same tomography. This is a micrometer particle, so it's a nanometer resolved tomography. So that's the kind of experiment you can find on Sirius. And we also use Wolfram Language to prototype the kind of data analysis that we want to do. Last but not least, I would like to show you our last project, this Orion project, is where we're building a biosafety level 4 laboratory to investigate pathogens of high periculosity. And we're basically this is the first BSL-4 laboratory in Latin America, and is the first in the world to be connected to synchrotron beamlines. So we are going to basically connect synchrotron to 3 X-ray tomography beamlines. One for looking at cells, small cells, in tomography with nanometer resolution, one for looking at tissue, and one for looking at small animals. But for optimizing the energy, you note that there are 3 different beamlines. Why do you have 3 different? Because depending on the thickness of your material, if it's a cell, is a tissue, or is an animal, then to reach nanometer resolution, a different dose is required. And you don't want to use a very high dose in this kind of systems because X-rays can damage them. So this is one way that we use also Wolfram Language in Mathematica to calculate the optimal condition given a thickness of a tissue. What is the optimal condition of energy and resolution and tissue thickness? Then how many photons? So this is a mode that is typically used in conventional equipment. So you can see 10 to the 15 photons required in some cases. But now with Sirius and with the coherent properties that we have, we don't need to use absorption contrast. We can use the contrast of a refraction of the X-ray, because they are coherent. We look at the wave front, how it's distorted in the material, and you can see that we can drop several orders of magnitude by doing the fluence in phase contrast. So basically looking at the wave front and using coherent properties of Sirius, and we can design these beam lines based on this kind of principles. So this is what I wanted to show you, how we use language, Wolfram language, to concept design, to narrow the search of heavy simulations, design magnets, designs where teams have to spend their major of their effort. We distribute executable specifications and examples in practice, like the ones I showed you. There's several other examples where we used this to specify systems on Sirius. When we go from using analytical models to reduce ambiguity and run detailed simulations to build and operate, as I showed you before. And to finish, the last slide. And I would like to thank you for your attention, and I'm open for questions. Okay, so we have one question from Les Butler. Great talk. I used the US lab Argonne APS 7BM a couple of weeks ago. I'm eager to see the APS Eberlite group add AI to the data analysis of plant root soils. Any comments? Yeah, in the Brazilian light source studios, we are heavily using AI to data analysis of plants and root soils. In fact, that's the only way we can do to analyze. We're working on a project now to analyze this soil properties, where we are heavily inclined to understand the soil properties of concreteness, of this cohesion that we call. But we need to analyze several samples that we collect in the field and to look at the porosity of the sample. So there's no other way. We basically use AI network. We use neural networks to analyze the pores density and the network of pores automatically. Otherwise, you wouldn't be able to do this kind of work. So we do use heavily, and I think in tomography this is very widespread in Argonne APS and in Sirius and many other light sources. So there's heavy use of this. How does researchers can learn and use Sirius? Daniel Carvalho is asking that. So we have courses for the researchers that want to learn to use Sirius. We run basic schools. We have one famous school that we have every year is Ricardo Rodrigues School of Synchrotron Radiation. Ricardo Rodrigues was the father of synchrotron radiation in Brazil, for those who don't know. And we run a school every year. It's a hands-on school that we have for 2 weeks. You can acquire all the basic learning. So stay tuned and look at our website for the next school. It's normally in July. And for those who are familiar with synchrotron radiation and want to more special courses on techniques on how to use AI, for instance, for tomography, we run workshops and specialized courses also, all of them in our website. Will this presentation be available? Yes, Kiran. I apologize. I didn't load the presentation before, but I make sure that this goes on. Yeah. Okay, Jason Albernetti is asking, is the Wolfram language used in any real time in any of the beamlines, diagnostic data analysis? Also, sorry if I missed this. What is the current of the accelerator? Okay, the current right now is 200 milliamps, is designed for 350 milliamps, which is foreseen in early 2027. We are installing a different instruments that we can bring the current to 350 milliamps. Right now we are running at 200 milliamps. No, we don't use Wolfram language in any real time in any of the beamlines. We have homemade software based. We rely a lot on GPUs and on CUDA, and we have groups that do the programming of the software that the users are using in real time. These are running on clusters with several GPUs. I mostly use Wolfram language to prototyping the kind of data analysis that we want to see in the beamlines, not in the applications directly on the beamlines. That's how we make the use nowadays today. Okay, since there are no further questions, I thank you all for your attention and for the great questions. And I'm available if anyone wants to chat more about Sirius. please contact me through the platform or through my email. Thank you very much and have a nice day.